So what were we looking at? So we were looking at big step semantics, and the problem that we are trying to do is again do factorial, right? So here is a loop-based factorial implemented using the language that we've just defined, whose semantics we've given by big step semantics because of this while loop. And we want to link it to and relate it to the intuitive definition of factorial expressed as a recursive program in Coq, right? And as we did for the transition system, so we are going to say something about the loop of the factorial. So all you're saying is that if you start with an output that is some number out, and you run the loop of the factorial, then the output variable at the end would be factorial of n, right? Where n happens to be the input, and multiplied by the output, the original value of the output. So we are going to prove this manually, right? So the way we are going to do that is by applying induction on n. So just like how we prove factorial, right? So let's induct on n and simplify. So you get the two things that you need to do, right? So the base case and the inductive case. So in the base case, the input is 0, so which is what inducting on n would give you. We do E exists and propositional to break this into two sub-goals. So let's do that. So okay, so now we have this. And if you sort of unfold the definition of factorial loop, which is just an example, which is the equivalent to definition, I have a while loop, right? Which is at the top. I mean, the whole program is just a while loop because it's just the body. And input is 0, right? So which means that the while loop body will not get executed. So I have to pick the right rule here, right? So if I apply E constructor, it would pick eval while true because of how E constructor works. It picks the first rule that unifies with the goal. We want to pick eval while false. We pick that. So now we are obligated to show that input is 0 in this V, right? Which is what we have here. Right? So if you simplify and rewrite using the hypothesis that we have here, right? So that goes through, and then the final result, right? So we proved something about the factorial loop. We want to show something about the output as well. So here, I mean, this turns out to be obvious, right? So output is sum out, and we have to show that if you look up output in V, then it is the same as sum out plus 0. So we rewrite, and then we apply f equal to remove the sum constructor, and we use ring to make the rest of the thing go through. I have this annotation here because I'll come back to this, but let's go through what we would do for the inductive case. So we do E exists propositional, right? So we unfold the factorial loop. We see the loop body there. So the idea here is that the input the input variable in the valuation is some n plus 1, and n is a natural number, right? So n plus 1 is greater than 0, so it will have to go through the true case. So that's why we call E constructor. You can equivalently apply eval while true here, but that is what is happening here, right? So if you apply E constructor, it is applying eval while true, which has 3 preconditions, right? So first, the predicate is not equal to 0, then you execute one step of the body, then you plug that in into the rest of the execution, right? And that is what leads to 3 sub-goals. First, we have to show input is, if you interpret input in V, it is not equal to 0, which is directly thanks to the hypothesis here, right? So if you rewrite using the hypothesis, n plus 1 is not equal to 0 goes through. So now we get to the body, right? So this is at the top level, this is one command, this is another command sequenced together. So when we call E constructor, we are appealing to eval, I think it's called eval seek. So, yeah, eval seek. So it breaks that up into 2 subcommands, right? These subcommands are connected by this valuation V1 here. So here, this is assignment. So E constructor picks the assignment that plugs it through. That's fine. Then again, this is an assignment, right? So again, E constructor that goes through. Let's simplify this because there is some computation here, right? So let's actually simplify that. So once you simplify it, it turns this into a big valuation, which is a match with and so on. But we know something about the hypothesis here, H and H0, right? So let's plug those values in because we look up those values here, right? So here and here. So you can rewrite using multiple hypotheses at the same time. So the idea is that you take both H and H0, you replace wherever you find the left-hand side, you replace that with the right-hand side. So that simplifies that a bit, right? And then one thing to observe here is I have a Sn minus 1 here, right? So this is n plus 1 minus 1. I know this is equal to n, right? So you can prove this as a separate lemma. You write a lemma which says for all n plus 1, n plus 1 minus 1 is n, and then use that to rewrite it to reduce the term. But a nice way of actually avoiding this extra lemma is using this replace tactic. This is a tactic that we haven't seen before. It's quite handy. It's not doing much, but it's handy. So the idea is that in the goal, right, if you have the term Sn minus 1, you're saying that replace that with n. And the way we are proving that these two can be replaced is by using linear arithmetic tactic, right? When you apply linear arithmetic, this is going to be, the goal is going to be proved, right? The lemma which says that for all n, Sn minus 1 equals n is going to be proved. So we're just saying use this tactic in order to first show that Sn minus 1 equals n, and then replace the occurrences of Sn minus 1 with n. It's a bit of a handy tactic that we can use. If you apply that, then this particular term, right, Sn minus 1 becomes n. Okay, that's fine. So now, if you sort of stare at what we have, right, we're saying eval, there is some valuation as an input, where the output is out times Sn S of n. Sorry, out times n plus 1, and input is n. And we have to sort of execute the loop body again, right? And we have to show what the, there is some existential variable that sits for the output valuation, right? But we know what the output valuation should be, right? In particular, we know that the output valuation is going to be input, and all we care about is that in the output valuation, right? So wherever the output valuation is, in the output valuation, the out variable, right, is going to be fact of n times out times s of n plus 1, right? So because that is what we have in the induction hypothesis as well, right? So if out starts at some out, then what you end up with is fact of n times whatever the out is. And because out starts at out times n plus 1, in the valuation here, it is going to be the case that when you look up output here, it's going to be fact of n times out times n plus 1. So essentially what we want to show is that I know what the valuation here is going to contain. So let me just plug that in. But there is no easy way to do that here, right? So what you could do is you could essentially take all of these assumptions, right? Write them down as a separate lemma. So assume this arrow, assume some valuation, some natural number, assume input has this type, out has this type, and this term evaluates to some valuation. And if you look up that valuation has an output value which is going to be fact of n times out times Sn, S of n, right? So you can explicitly write it. You can use that fact here in order to plug in the value for this, right? Just like we had this replace tactic, which was a helper tactic in order to avoid introducing a separate lemma. There is another tactic called assert, right? And the idea of this assert tactic is that you can prove, you can do assert P, right? And the idea is that you will first prove P, right? In under these assumptions, you will take under these assumptions, which includes this one as well. So what you're saying is, I will prove some proposition P, right? Under these assumptions. And once I actually prove it, because it was derived from these assumptions, that becomes part of the assumption as well, right? That become part of the hypothesis. So that is what we are going to do. And the reason why we are doing it is that we exactly know what is the nature of this question mark V here, right? And what we are going to do, the proposition that we are actually going to prove is, observe that I have a proposition here, right? I'm going to assert this proposition. This says there exists a V prime, right? Where if you evaluate in this valuation where output is output time Sn, input is n, which is the same as what I have here, right? The factorial loop, which is what is here, right? The loop is essentially what I have here. Then I get a V prime, and in that V prime, if I look up output, then the value of the output is going to be factorial of n times out times S of n, right? And why does this hold? This holds because we have induction hypothesis, which can be used to prove this, right? Because if you just plug those values in, you'll just get exactly the same term as what I have added as an assertion. But the reason to add this assertion explicitly is that we are going to apply unification to plug these value in, right? So we have to have a term which is precisely that. I can't directly apply the induction hypothesis here. That's the downside of having a more general term, right? And having a unification variable with which I want to unify. So I'm picking a particular instantiation of this induction hypothesis essentially. And I'm saying, okay, I'm going to prove it using whatever facts I have here. And then what I do is I say, okay, after this becomes part of the hypothesis. And then I will use that to unify with this. So let's actually do that, right? So I'm adding a assertion, right? So the evolution here is that I have two subgoals. Because I add an assertion, the assertion becomes the new subgoal that I need to prove. Okay, and I have to prove this assertion under these assumptions. So the assumptions haven't changed. As I said, this is a particular instantiation of induction hypothesis. So I can just apply the induction hypothesis. The induction hypothesis asks me to, it unifies with this first, right? It unifies with the term that I have here, right? This term, right? This term is the same as the term here. So induction hypothesis has other subgoals which I need to show. So when I apply the induction hypothesis, I get two more subgoals precisely corresponding to these two. And these can be discharged directly. So if you simplify equality, they go through. There is no other interesting behavior because the assertion that I added is a particular instantiation of the induction hypothesis. Okay, and then so here is one more tactic, right? So this is again a helper tactic. So there is a tactic called first order, which sort of applies, does all of the reductions that are possible in first order logic. Essentially, there is an existential variable here, so you can do E exists, and you can break this down into two subgoals, right? So if you apply first order, that is precisely what happens. So this E exists V prime. If you are in the assumption, if you have there exists a V prime, this can be thought of as an arbitrary X on which this property holds, right? So we pick arbitrary X, and the output V prime, which is the existential variable, is now replaced with X, right? That is replaced with X, and we also break this into two individual hypotheses, right? We break it into H1, H2, just so that this conjunction, right, breaks into two. This is just a helper thing. You could have as well done invert H1 here, right, which introduces the evaluation, and then you could have done, because conjunction is also an inductive type. You can always invert H2 to get the same result as what first order has done. But first order is just a handy tactic, I mean, it's just a handy tactic to discharge more complex first order logic simplifications. Any first order logic simplifications that can be done, it goes through. But observe that first order logic itself is it is undesirable, right? So you cannot, this tactic can go wrong, right? So it's probably not required at all in the rest of the lecture, but keep in the back of the mind that there is a tactic called first order logic. Just like propositional, this is first order. We need first order because there is an existential variable here. Okay, so we've done that. Okay, so now, okay, so what has happened? So let's go back, right? So before assertion, observe that we have H and H0, right? But after we actually prove these sub-goals, observe that this particular assertion, right, the assertion that we explicitly added here, right, in this part, is now appearing here, right? So that is what we wanted. We wanted a particular instantiation that we can then unify with. So first order simplifies it. Observe now that this factorial loop, right? So this is precisely this one, right? And this the input valuation here, whatever is expected, pattern matches this one, right? And hence this X can be unified with this, right? And the idea is that since X is unified with this, then this subgoal will be discharged, and the assumption that you will have is this one, with which you can prove if you look up output in X, then you will have this term, which is also true. But the thing that happens here is that you want to apply this, right? You want to apply this hypothesis in order to discharge this goal. It looks like it should, right? All of the terms unify. This unifies because it's the same term. The body unifies because it's the same body. This is a variable, unification variable, so that unifies with anything. So that should also unify. But of course, if you try to apply it directly, you get this error. You get an error which essentially says that unable to unify this variable v prime with x, right? Cannot instantiate v prime because x is not in its scope. Available arguments are whatever. So the downside of I mean, not a downside, but what Coq is complaining here is that when this unification variable was introduced, right? I did not have x in scope. Let's go back to the place where this unification variable was introduced. So we were here, right? There is no unification variable here. When we did the EX is propositional, this unification variable was introduced. One of the restrictions that we have is that when we introduce unification variables, they can only be unified with whatever was in scope at that point in time, right? You cannot bring up new variables. So the problem is that this variable that we have, X that we introduced here, right? So all of this happened. And then we introduced first order that sort of brought in X in scope. This X was not in scope when this unification variable was introduced. And Coq says that I cannot unify it with this X because you're just bringing up some X from somewhere. I don't know what that X property is, what it holds. So I'm not going to let you unify with that arbitrary X. But this is not a really big restriction here because we could have proved this earlier, right? So this assertion that we introduced, I just wanted to introduce it so that it makes sense when I introduce it. But really, before you actually bring that unification variable, this v prime in scope, I could have actually done this, right? So I just copy pasted this assertion and its proof to before introducing the unification variable, which got introduced here, right? The unification variable got introduced. The unification variable got introduced because of this existential variable at this point, right? So if I move the assertion earlier, I get the same thing, right? So if I just go to first order, I get the same thing, but except that now, right? Let's go to this position. Except that now, when this unification variable was introduced, X was already in scope, and Gawk says, okay, now I am allowing you to unify this. So if you ever have a error where you have a unification variable, you cannot unify that with some variable, right? Concrete variable that is as part of the hypothesis. You have to ask yourself, was this variable in scope when this unification variable was introduced, right? And by just moving the proof earlier, the proof of the assertion earlier, we have it in scope. So now if you apply H1, right, the thing goes through, right? So the change that has happened now is that the subgoal goes through. This question mark B prime gets unified with X, right? So this becomes just X. So that that's the trick there. In order to find the right place to introduce the unification variable, and then you can and this is very simple. So you have a equality, right? So you can use the rewrite, and then f equal to remove this sum, and ring tactic will make this go through because it can handle multiplications and additions. So that is the proof of right? So if you sort of stare at what we've actually learned in this, right? We learned a few things. We learned that there is this notion of an assertion that you can bring in, right? The idea is that you can assert arbitrary predicates under the assumption, right? This will avoid you to write complex lemmas where you have all of these variables and so on, just so that you can bring it as part of the set of assumptions, right? We also saw rewrite, right? Sorry, replace, which replaces one term with the other one. Again, simple terms, right? And by explicitly giving the proof for the equality, right? How do you show that this is equal to the other one? And the last thing that we saw is first order, which acts like propositional. It does while propositional does the propositional reductions. First order does first order reductions up to some point, right? This can, because first order logic is complicated. This might get into places where it can run into infinite loops. But I don't think we will see first order. We will see or have to use first order anywhere else. If it ever comes up, I will point it out. Okay, so what have we done, right? We have actually proved some property about um, the body of the loop. Now we have to prove the property, the property about the entire program, the factorial program. Right? And this is the intuitive property, right? So if if you start with the input n, the output will be factorial of n. Again, we do the simplification. We again have to show, right? So the idea here is that we start with an output that is 1, and if you run the factorial loop, then the output is going to be factorial times n times 1. This is true thanks to the lemma that we just proved here, right? So here we proved it for arbitrary output. We have to prove it. We are using it on a concrete output 1. So we assert it first, right? We'll just say I'm going to prove it, and the way I'm going to prove it is to just appeal the earlier lemma directly, right? So and this asks me to prove that output. So if you look up the input here, it is sum n, right? We know that thanks to the precondition here, right? So we know that we start with input that is sum n. and that output is 1. That is also true because it's part of the structure itself. That is what we assume. So these things go through. What we've essentially done is we have a particular instantiation that we can unify. Right. Again, this is precisely so that we can get it into a shape where we can apply unification. Right. So that is really why we use this assert here. So first order does the simplification as earlier, right? EX is propositional to simplify this. Okay, and then so if you unfold factorial, that's just a definition, right? So there is a sequencing here, right? So E constructor applies breaks it into 2 commands for C1 semicolon C2. The first command is C1, and the first command itself is the assignment. So E constructor reduces for the assignment that gets replaced. Now what we have is, I mean, if you do simplification, right? So what we have is if you start with a valuation where output is 1 and input is some n, and if you execute the factorial loop body, then you will get some valuation. I'm going to show that on that valuation, the result is fact n. This is true, right? We've just added an assertion that gives us the same thing. So so this matches with this one. We explicitly picked the assertion in the right way so that we can prove it. And the factorial loop is factorial loop here. This X will unify with this one, right? And this value will be useful in proving this second support. So just to show that they are the same, you can unfold factorial loop definition in H0. So you can use in H0 in unfold as well. So you sort of pick the particular hypothesis to unfold. This is not strictly necessary. I'm just showing it for reference. So that you can appreciate that the factorial loop here is the same as the loop here. And then you directly apply H0, right? That makes the goal, that proves the goal. And then now you have to show the subgoal. This is very simple. You do the rewrite using H1 F equal ring. So what we have done is we've actually proved that in the language that we've defined, right? So we defined our own language and we gave it our own semantics. And if you write the factorial program in this language, it will act the same as the factorial definition that we know in Coq. So the idea is this, right? So here we are sort of modeling something very simple, in the sense that this is a very small language. Of course, you can imagine writing complicated programs here, right? We write imperative programs which are not possible in Coq. So already we are modeling a language which has some features which are not present in Coq, right? We have while loops, we have assignments. Those are not already in Coq, right? So even though Coq itself does not have these features, we are able to describe the language, we are able to give semantics, and we are able to prove properties about these languages. I mean, this sort of forms the crux of what programming language researchers do, right? If you want to model a quantum programming language, then you say, okay, I will add certain features, right, which capture syntax first, right? I'll add some syntax to express these features so that I can write programs in this language. I will give meaning for this quantum programming language using an inductive type, right? Using this operational semantics. We are using big step here. We might use other techniques as well. But the idea is that you want to show that at the end of the day, you want to show that that does some useful thing, right? So what you do is you do something very similar to what we've done here, which is that you try to relate the result that is obtained by this quantum programming language on this program to something that you would say run on a traditional computer. Might just take like much longer on a traditional computer because you're iterating through the space. But for a proof point of view, that's not that's fine, right? We are not actually going to run that program. We are just proving that if you do this search on this complicated problem, then the primitives that you have assumed and the semantics that you've given for this quantum programming language, if they work as they should, as the semantic says they should, then you can get a result which matches your intuitive understanding of what the program should do. So that's the whole point of this, right? So of course, I'm sort of picking quantum as an example. You can do lots of other things. You can sort of course, Coq is not a parallel programming language. So you can imagine describing parallel programs, just like we've done in the previous lecture, right? Where we had a transition system that had two parallel threads. You can describe a language which has built-in parallelism, and then you give it semantics where you sort of say, here is how the parallelism works. What does it mean for a particular construct to essentially say, if you've done pthreads, what does it mean to say pthread create, right? When I say spawn this function as a separate thread, how does the execution go? You give that as part of the semantics, and then you can prove, right? So if you have a thread which is parallelly doing quicksort, that's the same as doing, say, insertion sort, and the result will be the same, for example, right? So you can do lots of interesting things like that. This essentially forms the crux of how we design and implement new programming features, right? What programming languages mean. So if you want to introduce a new feature, you would sort of think about doing this. This is not just academic enterprise, right? So WebAssembly, for example, which is like the standard for, and it's a low-level virtual machine language that is embedded in all major browsers today. So Chrome, Edge from and Firefox, and what's the fourth one? WebKit, the Apple Safari, right? So all of them implement a JIT, an interpreter or a JIT compiler for WebAssembly. And the idea is that typically these engines support JavaScript, right? But JavaScript is not a good target language. If I want to say compile Doom and run it on the browser, right? Doom is implemented in C++. So I want a target language that sits much lower. So WebAssembly, even though it has the word assembly in it, it's not an assembly programming language. It actually has higher level abstractions. But the semantics of what WebAssembly is defined in terms of something like this, an operational semantics. And this operational semantics happens to be written down on paper, just like how we've written down on paper, and it has a Coq formalization as well. So if you want to add new features to WebAssembly, you don't have to touch the Coq formalization, but there is an OCaml interpreter for WebAssembly language, right? For the WebAssembly language as defined as a formal language, you have to extend the interpreter with operational semantics and show that the new primitive acts in certain ways, right? It has some nice properties. It preserves type safety, or this is how it works. And then this becomes part of the reference spec. And then you go and implement the feature, right? So these things are actually used in practice. I mean, that is one. And the second one is, it's not just at the language level, right? So the language is sort of, and when we say programming languages, they're just everywhere, right? So it's not the languages that might, that is, and even WebAssembly is not something that a naive programmer would sort of write on a day-to-day basis. So they would say, I write C++, I will use a particular compiler to compile C++ down to WebAssembly. And I know how WebAssembly works. I have a formal spec. So I know if I compile it into this form, the operational semantics gives me a precise meaning of what will happen there, right? So the same holds true for modern architectures, right? So if you compile your program down to, say, native code, say x86 or the ARM instruction set, how do you know that the intuitive behavior that you have in mind for the program is preserved when executing on the machine, right? On this machine's ISA. So for like 50 years, right, we've just written English text. Oh, here is the instruction. Here is the state of the entire processor, all the registers, say the memory, right? And then you sort of say all of these control registers as well. And then when you execute this instruction, this is how it will change the memory. This is how it will change the stack. This is how it will change, say, all the registers. This is how it will change the control bits, and so on. this is very tedious and it's prone to mistakes, right? So what ARM has done recently, um, in the past 2 years, is to actually develop a formal spec that goes with the English text. So you have the English text. On the side of it, you have an operational semantics for the ARM ISA, right? The ARM ISA, you can sort of think about that as a language. I think it's also done in Coq. So you express the full ARM ISA in sorry, it's not done in Coq. It's done in it's done in this tool called Sail. Um, but the idea is very similar, right? So you sort of describe the ARM instruction set architecture fully as a language, and then you give operational semantics that explains how programs written in this ARM ISA should behave, right? I mean, you model everything explicitly, but you model it using this proof assistant. So it's not just English text, right? Whenever you write English text, it's very vague. English is not a precise language to describe um, very formal thing. And if you've read end user license agreement, you will know, right, on any contracts that you've signed. But these formal specs are sort of the gold standard. They're not for everyone. Um, but there are places like WebAssembly and ARM ISA where having a formal spec actually helps you in debugging, right? If you try to prove something, it doesn't go through because of the broken nature of the spec, then you can actually go and fix it, right? And we understand what precisely the meaning of a particular instruction set or a language is thanks to this operational semantics. So this is just scratching the surface, right? But the world there is sort of evolving. So this has all happened in the last 10 years. WebAssembly in the last 5 years. This ARM ISA moving to a formal spec in the last 2 years, perhaps, right? So this is exciting stuff, right? So this is not just like academic study. They are actively used in like large industrial settings as well. So that's what I want you to take away. Of course, I want you to take away about the minute details as well, but also have the big picture in mind, so that you the languages are everywhere. Deepali, question?
In the big step semantics, you said that the result is there when the program terminates.
Yeah,
But let's say I have written the function of the factorial using the while loop, and
yeah,
mistakenly it is not terminating.
yeah.
So, if I'm writing the proof, then how will I
Hmm.
understand when should I stop proving that because it's wrong?
Yeah. So the thing is, um, good question. So essentially, when we proved the inductive step, right? Um, the induction hypothesis sort of tells you the result is going to be reducing. So I believe it appears. Let's see. Um, so we induct on n. Um, so let's look at the second. So this is the termination condition, right? So we are assuming that n will terminate here, and we are making it go through. Will you get stuck here? If you don't do, oh, okay. So the place where it will come up is, um, let's go here. Um, so the thing is, input is input minus one, right? That is sort of changing the value of the input at every step. And if you don't have that, what will happen is what you're asking, right? If I make a mistake there.
Yeah, yes.
Okay, so um, I don't have an immediate answer. Why don't you try it out? I would say delete this line, right? So delete this line, right, and try to see where you get stuck in the proof.
Okay, okay.
Okay, so I think you will. The base case will go through because you are assuming that the input is zero there because we are doing induction on n. But the inductive case will not go through because you cannot prove that this will terminate. Try it out. I don't have an immediate answer. I don't want to give like a half-baked answer just to,
Yeah.
yeah. So try it out, and if you can let us know sometime, that will be useful, right? So see where it
Okay.
gets stuck. Okay, wonderful.
And another
Okay.
question is that can be means instruction means whatever that you have said that I say.
Hmm.
So it is more related to the hardware level. So
Yeah,
can we simulate such instruction sets in the calc also?
yeah, yeah. So we are simulating. So a good question again, right? So the language that we are describing here, right, has assignments, right? It has multiplication. It has assignment. So this assignment is not a thing that you can do in Coq, right? So Coq doesn't have anything that is similar to assignment. It has let binding, but that's different, right? So we are actually changing the valuation here. We have a while loop. Coq doesn't have while loop. We are actually giving semantics for what a while loop is, right? So um, you can give arbitrary semantics for arbitrary programs in Coq. You can describe features um, which are not expressible in Coq. See, the whole point is we are giving semantics for a program that does not terminate, right? And in Coq, all programs have to terminate. So we are going beyond what Coq can actually describe. And we are doing that by saying, by giving semantics in terms of inductives, right? We are not giving semantics in terms of recursive fixed points. We are not giving semantics in terms of a function, recursive function. We are actually defining an inductive relation that sort of says how commands relate to other commands. So of course you can give features, semantics to features that go beyond what Coq can express natively in Galena. We will see some of that towards the end of the lecture. We will actually describe a um, concurrent parallel language, right? So we will extend a small language with parallelism, I think the same language, and then we'll show how to execute things in parallel. Yes, of course, is the answer to your question. Good question. Anything else? Any other questions? I'll add pointers to this ARM ISA and WebAssembly um, in the Slack channel so that it's sort of you can have a look at it and see what it is. Um, okay, so let's move on. I think we have a few minutes, so I just want to start looking at small step semantics. Um, okay, so as I mentioned, right, so big step semantics will only give you meaning for when the program terminates. Does that mean that we cannot ever give some, we cannot ever prove properties about programs that do not terminate? The answer is no, right? So that's why we have small step semantics. And the idea with small step semantics is that instead of, see, observe that big step semantics always says what is the result of the program when this while loop terminates, right? Instead, the idea of the small step semantics is what it says, right? So I will just describe how the program evolves in a single step, just like a transition system. So the transition system might itself have an infinite loop, but I will just say, if you're in this state, the next set of possible states is described by one of these rules, right? And that just describes one step. And of course, the step might itself lead to the same state, but that's fine. I can still reason about the next step of the program. And that is what small step semantics give you. And it's infinite non-terminating programs are sort of very common, right? So if you imagine something like a web server is something that is not expected to terminate, right? It constantly waits on accepting new connections. It once you get a connection and a request, it satisfies the request, and then goes back to waiting. If you actually want to model these things, you cannot model them in terms of actually giving a result, right? This is not sufficient. Of course, you need I/O and other things, but that's besides the point. The point is, if you want to write programs, useful programs which have a loop in them, you cannot use big step semantics because big step semantics always tell you what is the final result in a single step. It is also unclear how to model concurrent interleaving threads. So what happens when you have concurrent program, right? You have 4 instructions here, you have 4 instructions here. So I want to say, oh, this thread can do one step, and then 4 steps of this other program can appear in the middle. So all of this requires you to sort of break up the program, um, not just reason about the program result, but break it up into saying, if I take one step, the state will be this, and this other two instructions from this program can happen, the other thread can occur. This is unclear how you would model any of that in the big step semantics, but small step semantics will let you do that. The key point is that it explains what happens in a single step, right? Um, yeah, it can model non-termination and concurrency. So we have the same language. We are just going to describe small step semantics here. And the common notation for small step semantics that people use is this right arrow, right? And small step, see, observe in the big step semantics, it started with the valuation command and just gave you a valuation at the end. Instead, small step semantics actually takes a valuation command and tells you what the next valuation and the command is going to be, right? So it's sort of takes the program state and gives you what the next program state is. In our simple world, the program state is the program that we are executing, the command and the valuation. So observe that we had a program which is skip, right? When you executed skip, you just return valuation, but we don't have an equivalent rule here. Actually, yeah, we don't have an equivalent rule, because when the program is at v skip, there is no step that you can take. You are just that is all. The program has ended. So that is why we don't have a rule that is equivalent to v skip goes to v here, because we cannot take a step from v skip. So that's not there. So what else do we have? We have assignment. So if you have v assignment of e to x, what you end up having is the valuation gets extended with the interpretation of e in v, right? And the command itself goes to skip. So you have to always give a command. So skip is like this no op, right? So we replace this command with skip. And if it's the last command, that's the last state. That's the final state in the transition system. So we stop there, right? And for sequencing, if you want to execute one step of C1, C2, then execute one step of C1. If so, the way to read it, let me take it back. The way to read this is, if the program is C1 semicolon C2 and the valuation is V, you can take a step from this one to V prime C1 prime semicolon C2 if you can take a step from V C1 to V prime C1 prime. The reason why I sort of took back my earlier definition and reset it is because you might not always be able to take the step. Because what if the command itself is skip, right? C1 is a skip. As we said, if the command is skip, there is no transition. So if the program is skip, you're just stuck there, right? So, but if the skip appears on the left-hand side of a semicolon, so if the program itself is V skip semicolon C2, then the step that you want to take is that ignore skip and continue executing C2, right? So that's what this says. So valuation does not get changed, but we go on to C2. Okay, and then for if, this becomes much simpler, right? So than compared to what we have here, because it's not a recursive rule anymore. It just explains the one step. If interpreting E in V is not equal to 0, then we have to execute the true branch under the same valuation. So in one step, it goes to VC1. And similarly, if E is 0, then you execute the false branch. And the way you say it is, in one step, you go to this other evaluation command where the state is now V comma C2. So you have to continue executing C2 here. And what is while? So the interesting bit of while is we have to, if the condition E itself is not 0, you have to execute one iteration of the while loop, right? The body of the while loop, and then you have to continue executing the while loop, right? And the way we capture that is we expand the command. So if interpreting E is E in V is not equal to 0, right? You have to execute the body once, right? C1, and you have to continue executing the while loop. So all we do is we utilize the fact that we have a sequencing command in our command language, and then say that you execute C1, then do the body again. So of course, this will have to sort of appeal to one of these rules, right? If C1 itself is skipped, then you go here. C1 is more complicated, then you apply this one. Then you will again come to the while loop. By which time you hope that the valuation has changed so that eventually E will go to 0. If interpreting E and B goes to 0, then this whole command is just skipped, right? So there is no effect. So that's the small step semantics, entirety of small step semantics. I want you to sort of compare and contrast with the previous definition, right? So we have, I mean, this rule is gone, but take time to look at how big step and small step sort of are related. So you have two rules here for sequencing. You have only one rule for sequencing. Why is that, right? Ask yourself why that is, and why is it described this way. Again, remind yourself why you don't have an equivalent of the skip rule in small step semantics. I think we'll stop here, and then we'll see the Coq encoding of the small step semantics. And as you can see, right, if you sort of look at it as a transition system, at the start of the program, you have the program to execute and the initial valuation, and this arrow describes the transition system. It sort of relates one state to another state, and you can keep doing this relation, and you can use the infrastructure that we built for transition systems to actually prove programs written using small step semantics, which we'll come back to later. And that's going to be sort of the rest of the lectures that we will cover on operational semantics. But there are two things here, right? There is the actual semantics that we describe on paper that is still useful. Don't just focus on the Coq one, because the assignments are going to be in Coq, but understand intuitively what is happening here, right? So I might, in the midsem, I might just say, oh, describe a language, small language, where you just write down a small step semantics, right? That sort of does something, or big step semantics that sort of does something. I wouldn't ask you for a Coq definition of it. So intuitively understand what is happening, right? So, and then it might be useful for you to sort of get that into the mind independent of the Coq definition. And for midsem, I think I won't ask you anything that is taught in next week. Okay, so whatever I cover until tomorrow is what I'm going to ask you about. Yeah, let's keep it at that. Okay, so let's stop here. I've taken lots of time, and then we'll catch up tomorrow. Thank you, everyone.